Okay. Auzubillahi minash-shaytanir rajim. Bismillahir-rahmanir-rahim. Assalamu alaikum, everyone. Today we are going to highlight the importance of settlement, and we all know from our previous lecture and in Geotech 2 that settlement is very important for the design of the foundation, because we studied in chapter number 2 about the shear failure criteria. Now, in this lecture, we will highlight the how we can find out the modulus of elasticity and what are the factors which will affect the modulus of elasticity to find out the immediate settlement. Then we will revisit and refresh our concepts which we touched in Geotech 1 related to the vertical stresses for various types of loading. So, as we all know, that foundation settlements must be estimated with great care for buildings, bridges, towers, power plants, and similar high-cost structures. So we need to estimate that with great care. Now, there are other structures which can tolerate greater margin of error for the settlement calculation if we do that. So, for example, fills, earth dams, levees, braced sheeting, and the retaining walls. So, if we do an error there, so it can be tolerated. Now, what are the problems which we face in settlement analysis? So, there are two major problems when we do settlement analysis. The first one is obtaining the reliable elastic parameters. And what are those elastic parameters? So the modulus of elasticity, which is used to calculate the or estimate the immediate settlement. Now, if we find out the modulus of elasticity in lab, and if we find out the modulus of elasticity in field, that would be totally different. And that difference is approximately 50% less you will find out in lab compared to the field one. Now there is another issue that in field tests we usually measure the horizontal modulus of elasticity. However, let me explain that here. So we are interested in the modulus of elasticity or the stress strain behavior which we get from the soil in vertical direction. But in case of the field test, which we are going to touch in a few minutes, so we lower those devices inside the borehole, and the horizontal pressures are applied, and the stress versus volume graph is obtained somewhere like something like this, and then we calculate the modulus of elasticity. So now if you see here, so the stresses are applied in the horizontal direction to the soil. However, we are interested in the settlement of the soil layer in the vertical direction, and we all know that the soil modulus of elasticity will be different in this direction and in the horizontal direction. So we will highlight those points in our today's lecture. The another problem is to obtain the reliable stress profile from the applied load. Now the reliable stress profile means that, for example, if this is the stress bulb beneath the foundation. Now, it's important to know that what would be the magnitude of stress due to that applied load. That is important. The second point is the depth till which the stress will occur. How much and till what depth we need to perform the to find out the soil properties, to find out the modulus of elasticities. So these stresses, magnitude and depth is also important in settlement calculation. Now, this slide, we are going to talk about the factors affecting the modulus of elasticity. So we will go one by one. First, method of laboratory test. If the soil in lab is confined, we will obtain a stress strain behavior and if it's confined, we will get stress strain behavior. And then if you want to find out the initial tangent modulus, call that EI, or if you want to find out at a particular strain level secant modulus, so we can find that using the E1, that's 0, and sigma 1, that is 0 as well. Now for the initial tangent modulus, this will be the E2, and here we will be having sigma 2. For the secant modulus, this would be sigma 2, and this one would be the E2. Now if you want to find out the modulus of elasticity, so you can use this equation to find out the modulus of elasticity. Okay, now the type of test, if it's confined, it will give us a different stress strain behavior, and if it's unconfined, or if we are performing a test in unconfined compressive apparatus or test, then the stress strain behavior would be different. If we are performing in undrained condition in a triaxial loading or drained condition in triaxial apparatus, the stress strain behavior would be different and the modulus of elasticity would also be different. Now for the degree of confinement, and if you remember that if we perform a test with 50 kilopascal of the sigma 3 or the confining pressure, and if we increase the sigma 3, and then again if we increase the sigma 3 to 200 kilopascal, so the stress strain behavior would be different. And the small strain range, usually there's not much difference there, but if you see the secant modulus of elasticity would be different, and that is also important, particularly that if we are interested in a particular strain level, that what would be the modulus of elasticity, and for that particular modulus of elasticity, what would be the settlement or the immediate settlement occurring at that particular strain level. So the degree of confinement plays an important role over consolidation ratio. So if I want to say that the degree of confinement increases, the modulus of elasticity increases. If the OCR increases, the modulus of elasticity increases. If the density of the soil is increasing, the modulus of elasticity will also increase. Now for the water content, if the water content increases, then the modulus of elasticity will decrease. For the strain rate, that how slow you are shearing your specimen in the stage 2 or how fast you are shearing your specimen in your stage 2 lab test. So if you're increasing the strain rate, this will increase the modulus of elasticity as well. And if the sample disturbance increases, the modulus of elasticity in lab will decrease. So these are several factors which you can note down. The effect of those factors on the modulus of elasticity. Also explained here that, for example, if we want to find out the initial tangent modulus. For example, if we perform a test and the stress strain graph look like this, there is another test and the stress strain graph look like this, there is another test which we perform depending upon the unit weight, water content, and the sigma 3 reconfinement, water content, and the unit weight. So we will get different types of stress strain behavior. Now, if you want to find out the initial tangent modulus, so you can simply draw a line, and then for those corresponding strains and stress level, using this equation you can find out the modulus of elasticity or the initial tangent modulus. Now there is a statement given here that if we want to find out the secant modulus, for example, the peak value which we got from the stress strain behavior is 90 kilopascal. So we can divide that in 3 equal increments. For example, 30 kPa and 30 kPa. So if we find out at 1/3 of this value, this will give us the ES, or the secant modulus of elasticity. We can also find out E50. For example, if we divide it by 2, that line, so if we divide it by 2, so E50 is also desired in few numerical softwares like Plaxis. Now, what are the lab and field tests used to find modulus of elasticity? So these are the lab tests: unconfined compression test, triaxial compression test, and these are the in situ test, which are the standard penetration test, cone penetration test, pressure meter, and flat dilatometer test will be discussed in our today's lecture. Iowa step blade and plate load test. Here it's shown that if we perform an unconfined compression test, then you will plot the stress and strain, and you will get the stress strain behavior, those points, so you will join them. And then if you want to find out the initial tangent modulus, so you can find out the initial tangent modulus, or if you want to find out at particular strain level using this equation, you can easily find out the modulus of elasticity from the unconfined compression test. If you want to determine the stress strain modulus or the modulus of elasticity ES from triaxial test, you need to perform unconsolidated undrained test, so we can control the drainage there. Consolidated undrained test, or cannot consolidated undrained test. What is cannot? That is lateral earth pressure coefficient, which is dependent upon the, or we can find out from the friction angle. U or C cannot U test can be performed. We already know that sigma H is equal to K naught into sigma V, and that K naught is dependent upon the V prime. The degree of confinement which I explained earlier on briefly, that if we increase the sigma 3, if it's 100 kilopascal, if it's 250 kilopascal, and if it's 470 kilopascal, then you will see that the strain behavior would be different, and the modulus of elasticity, or the secant modulus of elasticity, would be different. But at small strain, usually we will see that E value will be almost the same. Okay? Now, because of the effects of sample disturbance, it is preferable to determine E, or we can also determine the G, which is the shear modulus, which is also used in the foundation designs. Now, what are the field tests which are used to find out the E? So we can perform the standard penetration test or cone penetration test. They are widely used, but there are other tests as well, which will be explained in a few minutes. Why people prefer to perform the standard penetration test and cone penetration test? Because for various types of soils, various correlations, several correlations are available that they can use and to find out the modulus of elasticity. Please remember that here the term is used constrained modulus, and that constrained modulus is related to the modulus which we obtained from an odometer test. And why we call that constrained modulus? Because the load is applied onto that sample. Now the sample is constrained here, confined here from these three sides. Therefore, the modulus obtained from this test would be the constrained modulus. Again, value range for the static stress strain modulus for selected soils. For clays, glacial tell, loess, sand, sand and gravel, shale and silt, various values are the range, an approximate range is given that you can use for your numerical modeling. If you don't want to spend too much money on site investigation, so you can easily take those values, but it's always recommended to perform the site investigation in high value projects. Now, pressure meter test is one of the tests which is used to find out the modulus of elasticity in field, and there is a device which is lowered into the borehole, and this is basically the zoom in view of this portion where we are having a guard cell. In fact, we are having two guard cells, and this is the measuring cell. Now, this measuring cell will apply pressure onto the soil, and they call that soil under test. So once they lower in the guard cell and measuring cell into the borehole, then using the water pressure, this measuring cell will try to expand and apply stress on the soil or pressure on the soil, and we can plot that stress and volume curve or the pressure volume curve, and from this pressure volume curve, delta P and delta V, a change in the pressure and change in the volume, the modulus of elasticity can be estimated. There is a flat dilatometer test which is also performed in the field, so you can use the CPT rank. If you replace that with a cone, that would be cone penetration test. Now if you replace that with a flat dilatometer, for example, if you are looking from the side to this, so it will look like a line here, so it's pretty much flat there. Now here is a membrane, circular membrane, and high pressure nitrogen is used to inflate this membrane. For example, if high pressure nitrogen is used, now this membrane will try to expand and inflate, and it will exert pressure on the surrounding soil, and we will get the pressure volume curve from this test as well, and we can estimate the modulus of elasticity. Now at a particular depth here, now if we want to find out the vertical stress and we want to find out the sigma, I would say 1 and sigma 3, and at a depth of 4.5 meters, sigma 1 and sigma 3. Now how we determine that? We need to find out the sigma 3 of 20 kilopascal and sigma 3 of 40 kilopascal. So a method is shown here that, for example, if you are given with the friction angle, K0 condition, and if you want to find out the overburden pressure at the point A, that would be 34.6 kilopascal. Overburden pressure at 4.5 meter, that would be 80.6 kilopascal. Now the lateral earth pressure, we can simply multiply, which we already understood in Geotech 2. So we will come up with 14.7 kilopascal and 40 kilopascal for point 1 and point 2 respectively. Now once we get the sigma 3, so the stress and strain behavior can be plotted. And from these curves, we can find out the modulus of elasticity. And then we can find out the secant modulus from these two curves, and delta Q is the deviator stress which we obtain from the triaxial test. Once we get the E value, we can assume mu, or we can find out the mu or the Poisson ratio, and that epsilon L, which is the lateral strain, which we can find out using the lateral strain transducers. So lateral strains transducers are installed to find out the EL, and volumetric strain can be estimated using the back volume, which is used in the triaxial test. But we can assume the mu value of 0.5 for undrained condition, and mu is equal to 0.33 for drained condition, which is usually given in examples, problems, and assignments. Values or ranges of the Poisson ratios are also given by the Bowles in the Bowles book. Now, till this point, that was all about the modulus of elasticity, how we can find out the modulus of elasticity, how uh, what are the factors affecting the modulus of elasticity, what are the lab and field tests which will give us the modulus of elasticity. Now here we are going to refresh briefly your concepts which we discussed in Geotech 1. So we talked about vertical stress increases, that for example, if a load is applied, there will be a stress increase at a point which is located R from the central line and at a depth Z. Or in other words, if R and Z is known, we can find out the delta sigma Z or delta sigma X, okay, due to the application of the point load. Now, if we see here, and if the R is constant, which means we are going deeper, so the stress increase delta sigma will decrease as we go beneath the foundation. Similarly, if we want to go away from the central line of the point load, the variation of the stress increase delta sigma will look like this. If you want to find out the stress increase delta sigma, you can use this equation in which Q is this point load, R is the distance which is away from the central line, and Z is the depth of the interest at which we want to find out the stress increase. Now, researchers, they proposed an influence factor, or they used this term, this particular term, 1 divided by 1 plus R by Z square and whole 5 by 2. They call that as influence factor. And that influence factor we can estimate from a figure which will be discussed below. Now, if please kindly note down this equation, it's important. Now, if a line load is applied, and if we are interested to find out the stress increases at distance x, at a particular depth z, then you can use this equation where Q is the load per meter, z is this depth, x is the distance away from the central line, and you can find out delta sigma z and delta sigma x, or the shear stress as well, but you can note these two values because we are going to use it in solving examples. Now, if we are given with a strip footing, now the line starting from the left corner till this particular point x, and the line starting from the right corner here, this will make an angle alpha, and that alpha is being used in this equation to find out the delta sigma. Now, if we draw a line here, and we start another line from this right corner. Now the angle here, this will be beta. Now if the Q is here, that's the Q, you can find out delta sigma z and delta sigma x using these equations. Now in our previous lecture, we studied that for strip footing, the 10% of the contact pressure, for example, if 100 kilopascal is applied at this particular depth, what would be the Z value if we get 10% of Q naught, which means 10 kilopascal. So a derivation is provided here. If you simply use the strip footing equation for delta sigma Z, this one, so delta sigma Z is used, and that delta sigma Z is replaced by 0.1 Q, which is 10% of this load which is applied at a particular depth, but we want to calculate the depth because we already know that it is 6.5 B in the case of strip footing. Pressure bulbs or isobars are also shown here along the depth of the footing. Short problem from Geotech 1 is also included here, that we are given with the strip footing and B is equal to 2 meter. The uniform pressure Q is 250 kilonewton per square meter on the surface of a deposit of sand. The water table is at the surface and the saturated unit weight of the sand is 20 kilonewton per cubic meter, and the K naught, which is the lateral earth pressure coefficient, is 0.40. So if you find out the, so what is required, we need to determine the effective vertical, okay, sigma prime Z, and horizontal stresses, sigma prime X, at 3 meter, Z 3 meter below the center of the footing before and after the application of the pressure. So first we simply find out sigma prime Z, so it's gamma into Z, and then you find out that sigma prime Z, so you multiply with K naught, and if you use the strip footing equations which are highlighted there, so you can find out delta sigma Z and delta sigma X. Now sigma prime Z, this was the before the loading, but once you get the delta sigma values, now you need to add the before values here, and this is the after value. Again, this is the before value when the loading was applied, and delta sigma is the change in the load here. So you will come up with sigma prime Z and the sigma prime X as well. Now what if we are given with the circular area? So, and we are asked to find out the delta sigma or the stress increase which is occurring beneath the circular area. So if we are given with the circular area and we are asked at a particular depth Z that what should be the delta sigma value due to this particular load, or sorry, Q here, the contact stress is there. So please kindly note down this equation, Q 1 minus 1 divided by 1 plus R by Z square 3 by 2, and you can also find out the IC value from the figure as well, or you can calculate, if you know R and Z is given, then you can easily calculate the IC value, and usually Q is given So you can find out the delta sigma for a circular area as well. Now, there are two methods to find out the delta sigma. One method is the Bosnisk method for the rectangular area. So delta sigma is the stress increase. Now that Q naught is the contact pressure and M is the number of corners which are contributing to that delta sigma. For example, M would be 1 when delta sigma is under the corner of the footing. So M would be 1. And if we are asked to find out the delta sigma or the stress increase beneath the central point of the rectangular footing, then M would be equal to 4. So now in this case, M would be 1, and here it's M is equal to 4. I sigma can be find out using this figure. This is the I sigma figure. We need to find out the M into C and N into Z as well. So this is the M here, and this line shows, these lines shows N there. So if you want to find out the M and N, sorry, it's B. If you interchange these two, for example, if you write that N is equal to L by Z or M is equal to B by Z, so it doesn't matter because you will get the same value of I sigma. Now we can use the superposition concept, and that is the rectangular area. If we are asked to find out the stresses increase at this particular point A, so we can increase this area and we can divide it in 2. We will find out the M value and N value, and then you will again find out for this particular area, which is the increased area, and I would call that the stress increase for rectangular area using Bosnisk method. The sigma is equal to Q naught into M into I sigma there. So this would be the delta sigma for this. We need to find out, but we need to subtract this area or the stress increase which we got from this area. And the answer is given. Please kindly try at home. Use this equation, and the M is equal to and N is equal to the L by Z and B by C. There's another method to find out the stress increase, delta sigma. And please kindly note down this equation as well. That's Q divided by B plus Z and L plus Z. What is Q? The Q is the load which is applied here. And in slope 2-1 method, it is said that the stress increase we can find out at a particular depth Z. If we know the Q value, B, this is B here. Please confirm that you can hear me and voice is clear.
So clear.
Thank you. Now, this would be Z by 2. This will also be Z by 2. Okay. So this one would be B plus C. And if you are given with the square base, so you can use this equation. Now we will solve an example and problem that P load is applied, which is 375 kips. That footing is placed at 10 feet. The square footing is having length and width equal to 8 feet, and into 8 feet, this is 16 feet, and this is 10 feet. Okay, unit weights are given, relative weights are also given here. This would be 3.5 feet, and this would be equal to 2.5 feet. So simply use this equation and you will come up with the delta sigma equal to 1.11 kips per square feet. Now you will use the Bosenisk method, which is delta sigma is equal to Q into M into I sigma. Okay, close that. Okay, now you need to use the Bosenisk method to find out the delta sigma. Loads are given. Now, in order to find out that, you need to divide this 10 feet clay layer in 2.5 feet, and then again 2.5 feet, 2.5 feet, and 2.5 feet. So that's 10 feet there. We will find out different points, and once we get those points, we can find out the area 1 there, and we can also find out the area something like this, which will give us the delta sigma average, and that is desired. Okay, now we'll construct a table for Q naught equal to P by A. 5.859 is the kips per square feet. Now for different points, we will find out the delta sigma using the Bosenisk method, but in order to do that, the depth of this point here, please kindly note down that the depth is taken from the base of the foundation. So this would be Z1, and for the second point, this one would be Z2, Z3, and I would say Z4, and then Z5. So Z1 is equal to 6 feet, and Z5 would be equal to 10 here and 6 feet here, 16 feet. We will find out the M, and we will find out the N there, and once we get the M and N from that figure, we will come up with the I sigma. This is the I sigma, which is equal to 0.121. Then again you will find out the I sigma. We already know the delta sigma, and M is equal to 4 because we are finding out the delta sigma under the center of the footing. I sigma is given here, so we will find out those 5 values. Okay, 5 values of delta sigma here. Now As I mentioned earlier on, that we need to find out the delta sigma if we compare the area 1 to the area 2. So we need to use the Simpson rule, which we studied in numerical analysis. So this is the Simpson rule. Please kindly note down the Simpson rule here. So if we know the delta H, it seems like complicated, but don't worry, I will explain it here. Excuse me. Now, delta H is the interval, which is 2.5 feet. Here, delta sigma 1 is the value which we got at the depth of 6 feet. So this is the delta sigma 1, 2.84. Delta sigma 2, no, sorry, here is delta sigma 5. So delta sigma 5 is equal to this value, 0.63 divided by 2. And here delta sigma 2, which is this one, 1.81. And then delta sigma 3, which is 1.21. Delta sigma 4, which is equal to 0.86. So we will find out the area and then we will multiply it with the height or thickness of the consolidating layer. So we will come up with the delta sigma average of 1.404 KSF. Now this is a home assignment you can solve at home. It won't be graded there, but it's highly recommended that you use the circular 9 feet, and that 9 feet is chosen based upon the contact stress which is applied by the 8 by 8 feet rectangular footing. Rest of the parameters, soil properties are same, and you only need to use the equation which is mentioned for the circular area. So you can see R by Z, and 1 plus R by Z square, and 3 by 2. And if you want to find out numerically, you can subtract the column number 4 from 1, and once you get the Q and IC, so you can find out the delta sigma Z and apply the Simpson rule, and you can easily find out the delta sigma value. And you can clearly see the difference in the delta sigma. Slight difference is there, and that's because we find out first for the rectangular, and now we are finding for the circular footing. And this is the circular footing method. Thank you very much for listening very patiently. Now we will move towards the question and answer session.